what's amazing is these lectures are actually pretty darn independent of each other, except for that little thing. The one thing to know, and that is what a quaternion product is. It's just the scalars multiplied together, the dot minus the dot product, like happens with complex numbers, and then the scalar times the vector, vector times the scalar, and then the cross. And that's it. Okay, so we're going to do a little speedy review of what we covered yesterday. What I said yesterday was that I was a lunchbox physicist, and it says, oh, how beautiful and simple it all is. How could we have missed it for so long? And claimed that what I was really trying to do was to put time and space together. Now I'm going to give you something new out of that. Like, there's a big problem out there with the arrow of time. Actually, it's not a new problem. It was around since Boltzmann's day. And to me, the question is posed incorrectly. Because if you have a problem with time, I'm going to go by you in a spaceship, and I'm going to have now a problem with space-time. Because time is going to rotate in space, and now it's no longer a pure question of the arrow of time, it's the arrow of space-time. And so, is there a problem with an arrow of space-time? And it's like, well, the space part has got pointy fingers to it. And I can actually get a little bit more technical than that. I can show you the look. Well, actually, this is so small, it's easy to do. The Lorentz transformation for doing that it looks like this. And, you know, it doesn't matter how many times you hit things back and forth, it'll still be the same matrix. You'll still get the same results. You can play ping pong back and forth with flipping time forever. That's their arrow of time problem, okay? Now, if you try and do the same thing with the quaternion, and ever so slightly little bit of the cross product creeps in, that's the handedness, and that solves the arrow of space-time, which, as I say, is different from the arrow of time problem, but that's because I think the arrow of time problem is not the way to go. Okay, so now we'll kind of step through these slides, and we'll start with an executive summary, so we make this very simple. Executives like simple. Oh, great, I forgot. Let me just go back. I've got to have my amp on for you guys to hear this. Okay, so what we did was we went over numbers, you know, thinking about quaternions in terms of numbers. We showed you the little bit of algebra. We did a lot of equations, and I did have a few words to say about it all. Okay, so let me just make sure something's going on. Okay, that's great. No, we don't want to hear it twice. Okay, all right. So now we look at the linking of the math to the words, and we've got Euler-Lagrange somehow getting us from the back, what's written on the back of the T-shirt to the front of the T-shirt. I do have these little index cards that I'm trying to give away, just because if you do happen to wear the shirt, it might be a little frustrating. I've been in a situation where I say, well, you see that it doesn't work. But if you had a card, you can say, well, this little part here is about the symmetry of light and the weak force and the strong force, and anyway. So this is really an aid if you decide to wear the T-shirt and hope to try and explain things. Okay, so then it was the idea of merging complex numbers, scalars, and vectors using both I squared equals positive 1 and I squared equals minus 1 for hypercomplex and complex numbers respectively, or I should say quaternions. All right, so this was the graph theory that I came up with for quaternions and hypercomplex numbers, where the little clay balls are vertices and the edges are labeled, and they've got to go like I and minus I to kind of get back and forth, and then the plane is where it gets confusing because it's the cross product. But hypercomplex is easier and simpler, and that's related to gravity. So then we went ahead and derived the Euler-Lagrange equation, and I don't think the person who corrected me is returned, but I corrected the notes, and I just wanted to thank her. And even though that looks really, really scary, we notice patterns like the dA/dz going straight across there, and we've got all these duplicate sorts of things. So maybe we can deal with all those terms. We looked at Lorentz invariants, and I identified 4 that are on the back of the T-shirt. And then we went ahead and derived, in the right way, all 4 Maxwell equations. The first column is for E dot B, and it gives us the no monopoles in Faraday's law. And what's kind of neat about this graph is you can almost kind of think about how each one of those terms is used. It's one of these things like, oh, this must, in Faraday's law, this must be the E term, and this must be the cross term. But this example must be for X. This must be EX. And then we'll have this thing shift down for EY, shift down, and then those other boxes will shift around, and we'll cover everybody. So this is another way I'm trying to communicate the completeness of what Maxwell has done. And then we've got Gauss's law, which uses this b squared minus e squared Lagrangian, where the b's are separate from the e, so they're not mixing together and crossing each other, stamping each other's out. Then we went ahead and did what I'm calling the G field. This is only about gravity, where everything flips signs in this Lagrange density except the cross terms, and we end up with Newton's law down there. Rho equals, the Laplacian of a scalar field, and a time-dependent one, and that's very, very vital because it means that the time-dependent change in the mass density has time to propagate and be consistent with special relativity. Then I moved on to what's covered on the T-shirt. That would be the GEM field equations, and I call it an uber-modern Laplace's equation. So we're trying to do so much more than just say, well, it's just this one thing going on. And the math is actually easy, which is kind of nice. Okay, so then I gave you a flavor of group theory, and this one here has, I claim, U1 symmetry, SU2 symmetry, SU3 symmetry, and in a certain way, it's really about unit spheres in spacetime. We even made it out to the issue of spin, which is somewhat remarkable. And I was able to at least show you, and give you a sense of the angular momentum spin projection operator if I use jargon. And if I don't use jargon, I just said I got a 0 for the imaginary part because my 2 things canceled. And if you look at the coefficients, one of them had a bunch of 1s, another one they added up. And the ones that add up are spin 2. And that's symmetric curl. The ones that kind of look like they're canceling each other, there are only 1s involved, and that's curl, and that's connected to EM. And then sprinting hard at the end, we said that the exponential metric was a solution to my uber-modern field equations, and I think it's prettier because it is exponentials. And exponentials seem to dominate the world because they combine both doing absolutely nothing and doing a little bit of oscillation. And that's actually been an important kind of philosophical change that I've had, is I've always thought about physics as doing a lot, but it's like, the universe is like 13 billion years old, and if something is around after 13 billion years, it must be like basically doing almost nothing. And the key is, what is the smallest possible step from doing almost nothing? And I think that's what fundamental physics is really studying. So that is the review of what we covered yesterday.
So I wasn't here, but can I ask one question?
Absolutely. And by the way, anybody should do what this man's doing right now.
So on the shirt it says no stinking Higgs, which implies that you've got SU2 and SU3 in there, well SU2 in particular. Can you go over that again? Because I didn't see the SU2 symmetry.
I did not review that. No, I had SU2 symmetry in there. No, the no sticking Higgs was that was because there's a gauge field in this. Oh, I need this card. Actually, I need that T-shirt. Unfortunately, I have a few. Okay. It's larger than my card. All right. So the no stinking Higgs is based on an essential trick that happens in the standard model. You've got three symmetries: U1, SU2, SU3. In a certain sense, you need to preserve those. If you don't preserve them, what it means is that those charges are no longer conserved. If those things are no longer conserved, then some experimentalist is going to show you wrong. Okay? Because they actually do have experiments that show electric charges conserved to a super huge degree of accuracy. So, the way standard physicists do it is they say that vacuum is a false vacuum, and when I break symmetry from that, that's how some of these particles gain mass. Okay? I don't use that technique. Okay? My vacuum is completely real. There's nothing false about the vacuums that I work with. I think a vacuum really accomplishes nothing. Okay? Which turns out, ironically enough, to be radical these days. Because everybody uses the vacuum to get stuff done that they don't understand at this time. I'm going to hold the position that if I don't understand it, that's fine, but the vacuum will never explain anything in the universe other than like the volume shift. Yeah?
Sorry, how do you explain
electros? I don't think I do at this point. What I do on the T-shirt is say this term right here, this holding the T-shirt.
Was there adding a gauge field to explain why when you first
No. This is what I'm doing. It's a slicker trick than that. This stuff with the hypercomplex product that has a gauge field. So this thing has a gauge field. I think this is related to things that deal with gravity. This thing also has a gauge field. Okay? So this also applies to things with mass. But this is a plus and this is a minus. So the two gauge fields exactly cancel.
I still don't understand how you explain spontaneous, how you can justify throwing out spontaneous, justify all the experiments you're throwing out.
No, what I'm throwing at, the one that I'm trying to throw out is the Higgs particle. There is no data for the Higgs.
No, but there is data for the fact that we don't use
I know, and I'm consistent with that because this equation has a gauge field.
Okay, that's what I'm saying.
Oh, okay. Sorry. It's just that this gauge field exactly cancels that other gauge field. It's that I have two gauge fields. One for the standard model stuff and one for gravity. That's probably where I bring it in. There's a gauge field for gravity. And it's the gauge field for gravity that cancels the gauge field for the other three forces. Is that closer? Is it closer to making sense?
Yeah.
Okay. All right. So, what we're going to do now is try to address the question why quantum mechanics is weird. And there are a variety of schools for this. And And in fact, I went to a talk by Max Tegmark where he took a vote on what people preferred, which is kind of funny, right? To me, that's a sure indication that physicists haven't settled on an answer, okay? And in fact, in this group, it was at Harvard University, it was, the Copenhagen got no votes. It was like, wow, the Copenhagen interpretation really is not popular. Oh, who was it? Who was the other guy? Oh, my brain's going a little dry. What?
Everett?
Yes, yes. Everett got a lot of votes, and so did, who was the other person? Anyway. But it was kind of curious that Copenhagen got no votes. But physicists still are not at peace. And I said, I do have a different answer, and I'm going to go through the logic of my thing. And what it is that if you do quaternion calculus correctly, that I think that provides a new answer to this old question. So, is quantum mechanics weird? These are probably the most famous quotes out there. I don't know, maybe I will read it, just whatever. So from Niels Bohr, it says, for those who are not shocked when they first come across quantum theory, cannot possibly have understood it. More modernly, Richard Feynman says, I think I can safely say that nobody understands quantum mechanics. And then Albert Einstein said something like, God does not play dice with the cosmos. And Niels Bohr retorted, do not presume to tell God what to do. And Groucho Marx even had a comment in there, very interesting theory. It makes no sense at all. So I thought we'd go a little bit deeper into Richard Feynman, since I have so much respect for him. We have always had a great deal of difficulty understanding the worldview of quantum mechanics represents. At least I do, because I'm old enough man that I haven't gotten to the point where the stuff is obvious to me. Okay, I still get nervous with it. You know how it is, always is. Every new idea, it takes a generation or two before it becomes obvious that there's no real problem. I can't define the real problem, therefore I suspect there's no real problem, but I'm not sure there's not a real problem. So I think that's nice because it shows the tension in his mind. And let's face it, this guy won a Nobel Prize for QED, so he was good at quantum mechanics, and yet there was like a pea under this pile of mattresses that he was sensitive enough to still feel at that age. And based on, I don't think we've solved it to this day.
So the problem, just to define it, is
yes?
the non-unitarity of quantum collapse. Is that fair?
I would say that's probably too technical an answer. I mean, maybe that's a way to look at it. I think it's like things like the uncertainty principle. It's like, how does that really work? Why is that there? I think it's almost as simple as that. But if you start to get into Dirac's equation, you go, well, what's a creation and an annihilation operator really doing? Explain that to grandma. I might explain it to a graduate student in physics, but not grandma. Okay, so I'm arguing basically that quantum mechanics is still weird today. Einstein, I think his views are, everybody wants to say, Einstein thought just like I did. It's like, no, that's not the case. I read a very good, The Subtle is the Lord is a wonderful book about Einstein and his philosophy and actual science. And he was impressed with what they did. You know, the Bohr atom was just spot on. But Einstein thought a lot about causality. Why did this happen? How could this have happened? And that's, I think that's the P under his collection of matrices, is what is different about causality for quantum mechanics than classical. I mean, classically, A happens, then B happens, and C happens. Okay. Well, this is a little picture of what goes on. That only the sum of all possible histories says what happened in quantum mechanics. So there's this guy looking at the moon, it's bouncing off of a lake, and if you actually decide to focus on just one path, you'll get that signal. It might not happen very often, but it will happen. But if you go ahead and calculate what happened, what you need to do is out of every single one of those, you'll notice that one of those actually happens a lot more often. It's not destructive sort of thing. But you must include them all. And that, in essence, is kind of odd. I gave this one kind of its own space, and that is that the math of quantum mechanics is flawless. It's used to make the most precise calculations out there. So I'm not challenging that issue. I guess it's not an issue. It's great math. And it's like, when we get away from the philosophers, and we just say, we got to do these calculations, everybody's with the program about how it is done. So my list of the largest 2 new math ideas generated over the entire history of physics is calculus by Newton and spacetime by Einstein. And I probably should give Minkowski credit because he was the guy, he was his math teacher and said, you're really rotating time into space here. All right, so I'm going to try and smash the 2 biggest ideas together to make Quaternion space-time calculus. And I take this right out of my calculus book from the day, and it just doesn't work. It doesn't work because quaternions do not commute. So should I write that dq on the left, or should I write it on the right? Now, there are professional math wonks who work with quaternion derivatives on the left, or maybe they do it on the right. I don't know which is actually more popular in the literature. But either one I consider a disaster because, for technical reasons, they can't show that q squared is analytically q, and it's like, well, then why bother? If you can't figure out the polynomials, you can't figure out anything. If you can figure out the polynomials, you can figure out everything. So I consider it a complete train wreck. And so I thought about an alternative. It's basically the 3-vector part of the differential element that goes in the cross product. It's the cross product that makes it not commute. So why don't I just make that go away? By being clever here, I'm going to take 2 limits, one after the other. I'm going to first let the problem child go to 0, and then I'm going to let the time go to 0. Okay? That's a well-defined sort of animal. And it's it's a variation on L'Hospital's rule, which I always consider a little miracle when I first learned it, about taking two limits in order to get something that actually is valid. So after dr has gone to 0, dt, the dt part, commutes. And so maybe it doesn't matter if I write it on the left or I write it on the right, as long as I use 2 limits just like this. So we're going to test it. We've got this function q squared, and we're going to use that the limit definitions. And I don't know if you remember those calculations from, hopefully you did those in high school or something. But it's kind of fun to see them actually kind of work out. So the first line I just say, okay, I've got q and I'm adding in my dt, my differential element. And I'm subtracting off the q without the differential element. And I'm dividing it, maybe on the left or the right. That wouldn't make a difference at this point. But now I just kind of crank through that multiplication, and I've got q, the differential element, and then the differential element q. At this point, they are different. And then when I let dr actually go to 0, then this guy right here, it doesn't matter whether I write him on the left or the right, because he's just a real number. And since he's the inverse of that, he's going to cancel that one. He's going to cancel that one. I'm going to end up with exactly dq, 2dq, and a differential element. And so when dt goes to 0, I just get dq. I mean, that's what you expected, okay? But it required this two-limit trick. If that two-limit trick isn't there, it does not work. Okay, so with our physics hat on, okay, we say if dr really being a change in space is less than c dt, then things are traveling at less than the speed of light. Okay? And so in a certain sense, I think of mathematical physics as being a little bit more constrained than math is. Well, because, yeah, that's a kind of more philosophical sort of thing. And I call this a timelike derivative. And only by me, this isn't like, I know I've had some people who were doing reviews of quaternion derivatives that are out there in the journals, and actually twice people have said, you know, I happened to stumble upon your definition, and I really liked it because it was really simple, you know, and it seemed to work. Where those things got published, I have no idea. But yeah. Anyway, so that's that story. But then you go, well, how about the other case? What happens if the change in space is larger than your changes in time? Then don't I like have a problem? It's like, yeah, you do. That guy, what can I conceivably do with that? That's still going to have this this cross product problem. Okay, that doesn't. Shouldn't nature also use that situation? And I think the answer is yes. Okay, but how does it use it? And this was my idea, to say that the norm actually does not depend on the cross product. Doesn't show up there. Okay, so if I take the norm of these derivatives, that is well defined. If it's written on the left or it's written on the right, the norm will be the same. So you may not have dealt with norms of derivatives back in high school or even in college, but I mean, it should be okay. You're going to get less information though, right? You're just going to get the size of that change. You're not going to get a sense of its direction. But this is all you can do, is my perspective. So we'll test on the same function. Okay? Now the first two lines, there's really no difference except the order of the limits. Okay? Then you write it out and you go, oh, okay, so now I don't have time around anymore. I just have these sorts of these terms here. And he's like, well, how did you go from line 3 to line 4? The way I did that is I said, well, I'm just dealing with norms. And the way norms work is the norm of one times the norm of the other just equals, the product it goes to. It's just really, really that simple. So I'm taking the norm of that, the 1 over r thing, and when I take the norm, it will just be a real value. It will just be a scalar value. So I can commute the norm of that thing. And if I commute the norm of that thing, then I'll be able to get a 1 out of there, right? I'll be dividing the norm of this by the norm of that. Well, that'll be 1. And so 1 times that, I'll just get the norm of that. I'll just get the norm of that, or 2 times the norm of that. And so that's the result there, is that it's the square root of 2 q star q in the limit. So the timelike derivative and the spacelike derivatives of the same function actually give you different results, which isn't that surprising, right? Because the different, well, I don't know whether it's surprising or not, but what I'm thinking here is that classical physics is the normal derivative where you let space go to 0 first and then time go to 0. Whereas quantum physics has all these norms showing up because you have to take the norms of all these differences. And as I say, I don't think there's a testable difference with this definition of these issues. And so that's why I don't like get up on a soapbox and bang on it. I mean, I feel warm and fuzzy about it. But if I don't have an experiment where they can say, hey, if you do this, it'll give you this different answer. Actually, what I did do was I went to that talk by Max Tegmark and warned him that I was coming with my own approach to it, and tried to do this calculation on a piece of paper. He asked me to actually do it, and I wasn't able to spin it up. So, and in fact, one of the things I'm most pleased about from this whole lecture series was figuring out not only that one, but the calculation there. That was a new calculation for me. All right, so and we'll actually get some visuals of this, amazingly enough. So why haven't we heard about this particular idea? Because it's a mashup of complex numbers, vectors, and the limit definition of derivatives. And that's a lot of things to mash up. And not enough people work with quaternions in the first place, so you got worried about the definition of quaternion derivatives.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil.